Welcome to Chemistry with Caroline. In this video, we're going to look at how to identify electron withdrawing groups when attached to an aromatic ring, how they pull electron density out of the ring, and what carbon atoms in particular are going to be electron deficient as a result of those groups. So we'll go over resonance and induction, and then how to spot and identify electron withdrawing groups. So generically speaking, the electron withdrawing group pulls electron density out of the ring. So that ring is going to be electron deficient compared to just like a normal benzene ring. And that electron density can be pulled out of the ring either via resonance, which is talking about the pi system of the molecule, or via induction, which is more the unequal sharing of electrons through the sigma framework. So electrons that are in single bonds that are shared unevenly. This is nitrobenzene. It is a benzene derivative that has a very strongly electron withdrawing group, the nitro group, on it. So I drew the condensed formula up here. Oftentimes students will think, oh, the nitrogen's attached to the ring, so that's an electron donating group. In this particular case, this nitrogen has two oxygens on it, and so it actually has a full positive charge. It doesn't have any lone pairs of electrons, so it's not a donating group, it's a strongly withdrawing group. So that positive charge is going to be drawing electron density out of the ring. The pi bond that's adjacent can come up and make a new pi bond there, and these electrons can get pushed out. And that will give me a structure that looks like this. So I'm going to have a high overall charge in terms of like each atom on my ring, but my overall formal charge is still going to be 0. But you can see I have 2 positives and 2 negatives. So now once I'm in the ring, this charge can go around the ring. And now it'll go back to the other side. And then lastly, one of my lone pairs on one of the oxygens can fold back in to give me the resonance contributor with the lowest overall formal charge, kind of like the one we started with, but you just got your pi bonds alternating there in opposite positions of where we started. So we draw resonance contributors like this with Lewis structures to show us all of the ways that electron density can be distributed throughout the pi system, but the molecule is not existing as one of these or the other. It's a weighted average of all of them. It's sort of a hybrid of all of them. But when we draw out our resonance contributors with Lewis structures, we can see what atoms are electron deficient and what atoms are electron rich, and that gives us a sense of the overall character of the molecule. So this particular ring is going to be electron deficient. We can see that in the resonance structures, this group is pulling electron density out of the ring. It's circulating a positive charge around the ring, and the ring is going to be electron deficient. So this benzene derivative, trichloromethylbenzene, is a electron withdrawing derivative as well, and it is withdrawing via induction. So there's no ability to take electrons out of the ring because there's no ability of that carbon that's directly attached to the ring to accept electrons. It's sp3 hybridized. It doesn't have an empty p orbital or a pi bond that can shift in order to accept electrons. So this is just via induction through the sigma framework. All those chlorines attached to the carbon are more electronegative, and they're pulling electron density away from it. But it's not just the one bond. It's sort of from all the bonds that are nearby to a lesser extent, but proximity matters. So overall, there's electron density being pulled away from that carbon. It's going to have a pretty substantial partial positive charge on it, and that's going to pull electron density out of the ring. So this is via an inductive effect. So if we make a list of electron withdrawing groups, and we'll start with the most electron withdrawing group. That is the nitro group that I showed you in that first example. It has a full positive charge on the nitrogen. It's really pulling a lot of electron density out of the ring, and it can do that via resonance. Next up, you have this SO3H group. So a sulfonation reaction would produce a substituent like this. And that sulfur has a resonance contributor where it has a full positive charge on it, and it also pulls electron density out of the ring. Then you've got carbonyl derivatives. So I'm going to put an X on the other side of this because really it could be any carbonyl derivative. So the amount that is withdrawing is going to matter a little bit depending on what X is, but it could be H, C, O, N, any of those carbonyl derivatives. In all these cases, you have groups that have electron density being pulled away from them. And in the case of any carbonyl derivative, you're going to have a resonance contributor through that because you can pull electron density up onto the oxygen there. Then you would have like a cyano group. That's another one. Nitrogen is a little bit less electronegative than oxygen, so the pull is going to be less, but it can also participate in resonance. And then the last one is going to be through that inductive effect. So like a CX3. So X is going to equal a heteroatom that is more electronegative than carbon. So it's creating a partial positive on this carbon right here. So all of these top groups are able to participate in resonance. So they can actually pull electron density out of the pi system, out of the ring via resonance. This last CX3 group here, this is just an inductive effect, which is not quite as pronounced an effect. And so the electron withdrawing capabilities are not going to be quite as large. And again, the type of group that's attached to your ring is going to have implications for its reactivity. With electrophilic aromatic substitution reactions, this can impact how reactive the ring is and where the new group is introduced. It can make a ring more susceptible to nucleophilic aromatic substitution reactions. When we think about proton NMR spectroscopy, the type of substituent that is next door is going to influence the chemical shift of those proton signals that you would see. So again, you have a basic principle that is wide-reaching in its implications across all of these different applications in organic chemistry. If you found this video helpful, please like, subscribe, and share with your friends, and I'll see you next time.